Hey everybody. Okay, cool. You can hear me. Thanks for having me here, and thanks for joining. So today I'm going to be talking about how cybersecurity enables blockchain applications and how you can use blockchain to build cybersecurity products and marketplaces and advance cybersecurity interests as well. But the core thing that I'm getting at here is nothing that you build on top of blockchain is really viable if the security isn't solid. So we're going to take a dive a little bit at the beginning of this presentation, diving into some of the vulnerabilities that we've seen in various layers of the blockchain stack, and see where people went wrong and perhaps how we can do better in the future. And then in the second part of the presentation, I will be taking a look at what you can use blockchain for in order to build cybersecurity products and services. So first part here, okay, here we go. Why is this not working? Okay, so let's talk about security enabling blockchain. So like I said, we're going to take a look at some of the different layers in the blockchain stack. So starting from the top, we're going to take a look at some Ethereum smart contracts. A lot of blockchain technologies, a lot of blockchains nowadays support the notion of smart contracts, but Ethereum is definitely the most widely used and also most often exploited. So we'll take a look at a few examples there. After that, we'll talk about blockchains themselves, exchanges that make blockchain viable for the vast majority of people, software and hardware that you use to access blockchain applications, and then we'll move on to the second part of the talk. So let's start at the top. So smart contracts. So a lot of things have gone wrong with smart contracts in the past. And one of the things I want to drive home with this presentation is we need better tooling. We need safer languages, first and foremost, I would say, to remove some of the foot guns associated with building smart contracts. So let's take a real quick crash course on Ethereum. So Ethereum supports this notion, like I said, of smart contracts where you can not only send cryptocurrency between people, but you can also write programs that execute on the blockchain that govern how funds are allocated or taken and moved and things like that. So these are actual programs that are running in this distributed network, actually computed by the miners in the Ethereum blockchain in exchange for reward, namely gas, is what it's called in Ethereum. So much like you need gas to run a car, you need gas in Ethereum to execute smart contracts. So that's kind of the high level here. So let's take a look at so all of these contracts, they're defined by the Ethereum yellow paper. For some reason they made it yellow. I'm not really sure why. I want to be a little special, but there's a specification for these contracts, and these contracts, they're written typically in a high-level language called Solidity, and compiled down into EVM, or Ethereum Virtual Machine, bytecode. And that EVM bytecode is actually what's executed by the Ethereum nodes that are making up the network. And there's a little example of some bytecode there that's been disassembled. And you can think of it the same way as x86 or ARM or maybe even Java bytecode that somebody's taking a look at and trying to reverse engineer and find vulnerabilities in. So Solidity in particular, again, that's the most popular high-level language for coding Ethereum contracts right now. Solidity's had a number of issues in the past where they made it effectively very easy to build vulnerabilities into these smart contracts. There's efforts underway right now to replace Solidity with something called Viper, which draws its name from Python. It's trying to be Python-esque, and it removes a lot of the pitfalls that you would have with Solidity, so you can produce more secure contracts without thinking about it. So let's see. So I'm going to run through a few examples here of some smart contracts that have had issues in the past. This one I very much like because it actually demonstrates something that Solidity fixed. So again, moving towards safer languages and fixing and removing different ways for a language to allow developers to build in vulnerabilities is really what we should be moving toward, right? Addressing specific vulnerabilities is kind of a game of whack-a-mole. If you're familiar with that game, there's fires popping up all the time and you're just putting one out at a time. So really we need a better fire department, which is a more secure language in this case. So in this example, somebody wrote a unabashedly pyramid scheme on the Ethereum blockchain. So there was this smart contract called Dynamic Pyramid, which did exactly what it purports to do, which is namely, you get more people to invest in this pyramid scheme after you do, and then you get some sort of payout based on additional people putting funds into this system. So somebody copied this Dynamic Pyramid smart contract and renamed it to Rubixi. And Rubixi does exactly the same thing, just with a different name. And the reason why this became a problem is they failed to rename the smart contract in all of the places that they needed to. So they renamed the name of the contract to be Rubixi, but the name of the what should be the constructor function, which is a function that is called once when you deploy the smart contract onto the Ethereum chain and should never be called again, and can never be called again, to be more specific. Because they did not rename the constructor function to also be Rubixi, it was not considered by Solidity to be a constructor function. So it remained callable after the fact. So what does that mean? So here's one of the simplest sort of vulnerabilities you'll see here. So what you're seeing is at the top, you have the contract named Rubixi, and then you have a function called Dynamic Pyramid, and Dynamic Pyramid, that's not the same string as Rubixi, so that's a normal function now. And by default, in Ethereum smart contracts, normal functions can be called by anyone at any time. And this function reassigns the variable creator to whoever called that function. Message.sender is whoever called that function. So in order to drain this pyramid scheme of all of its money, you simply needed to call the function Dynamic Pyramid, set yourself as the owner of the contract, and then just withdraw everybody's funds. So here's a good example. And I wanted to bring this one up because this actually is impossible in Solidity anymore. So this is something that was possible, but if you're using a moderately recent copy of Solidity, you have to actually explicitly say which function is the constructor. So this is not a mistake you can make anymore. On the note of safer languages, there's a push for this in a lot of different spaces right now. So I'm going to get to C++ in a little bit. C++ has a lot of foot guns as well. More commodity sort of software is built with C++. We have browsers. We have, thankfully not kernels, that's C, but even still, we have a lot of code, mail clients, et cetera, that are written in C++. So Mozilla, the company behind Firefox and Thunderbird, has been slowly porting over their browsers to a language that they developed called Rust. And Rust provides a lot of different promises in terms of you cannot write past the end of a buffer. You cannot express a vulnerability, you cannot express a use after free, for an example. Just due to the way that their borrowing system works. So this is what we need to see more for blockchain. So show of hands real quick. Has anybody here ever played the game Rocks, Paper, Scissors? There you go. Yeah? Okay. Fair number of people. So one of the key aspects of Rocks, Paper, Scissors is you need to not know what the other person is going to play before they play it, right? Sounds kind of obvious. Somebody built a rocks, paper, scissors smart contract on Ethereum and failed to attain that objective in this game. So what happened is because they by default in a blockchain environment, everything's public and it's public forever. And, there's this immutable ledger, which is great for some aspects, not great if you're trying to play a game that involves secret data. And this secret data in this case is what the other play is going to be from the other person. So in this case, if you were running in a full Ethereum node, you could see what your opponent played before their play was mined into the blockchain. So imagine playing rocks, paper, scissors, but you know what your competitor is going to say. So you can play the winning play every single time. So your competitor plays scissors, you play rock, bam, you win. So what they didn't take into account here is the fact that, again, everything on the blockchain is public. So, having better tools in terms of keeping things private and some other, not Ethereum, but, well, maybe Ethereum, I don't know, but some other, blockchains are building convenient sort of private labels on data that are used inside contracts to do things like a commit reveal sort of scheme. So I always bring this example up, because it's maybe one of the more, prominent ones. So early on in Ethereum's history, there was something called the DAO, the Distributed Autonomous Organization, where they were trying to set up this community-owned and operated organization where people would vote on the blockchain for what this organization was going to do. Its first product was building a Ethereum-backed smart lock. So think like Google Nest or something, but you would send some message on the Ethereum blockchain and you'd wait 5 minutes for your door to unlock or something. Anyway, so the DAO was backed, this distributed autonomous organization was backed by a contract on the Ethereum blockchain, and that contract was designed to govern how this organization would operate. Part of this contract was it allowed people to create child companies, child distributed autonomous organizations from it. And the vulnerability here was they would call, they used something called .call.value, which actually passed execution from the DAO contract to wherever it is that they're calling to. So if they called from the DAO into an attacker's smart contract, the attacker's smart contract would now be executing as if it was just a normal function call from, a normal program. So say your web browser calls some random untrusted code at some point. That's effectively what's happening here. So what people did to exploit this is what's referred to as a reentrancy attack. So people drained the DAO for between $50 and $60 million US at the time. And the way that they did this is they continuously split the DAO, and they had the DAO do a .call.value to their malicious contract, which called back into the split function. And that split function happens before balances are adjusted. So you see at the bottom here, it's adjusting the total supply and also the balances of the person calling and the amount paid out. But it's annotated as 3 above that. Withdrawal reward 4 actually in that function does a .call.value to the attacker's smart contract. So what they can do is when withdrawal reward 4 calls into the attacker's smart contract, they just call this function split DAO again, and it executes again, sending them additional funds every single time. So they think of like a stack overflow where they're recursing all the way down, draining the funds out without ever actually hitting the operative code where it zeroes out their balance, ensuring that they can't do that. So another thing that's happened in the smart contract space is honeypots. So honeypots are kind of fun. People go out and they try to exploit Ethereum smart contracts using things like reentrancy bugs to do so. And so people have kind of gotten wise to that and set up honeypots, which are contracts that look vulnerable, but they actually aren't. So they get, malicious people on the internet to basically try to steal funds out of these contracts that end up actually stealing the funds of the people that are trying to steal the funds. So it's a little bit of a, hacking back, so to say, I guess, but in a more passive sort of manner. So there's my coworker actually at a previous Hack in the Box event, we ran a competition called HODL Wallet that was a honeypot that looked like it was vulnerable and it actually wasn't. And these slides are going to be available afterwards. I'm going to skim through these real quick, but happy to answer questions after in terms of how this works. But, because I have a lot of slides to get through. But in some, while this does look vulnerable to the same sort of reentrancy attack that we saw before, where the withdrawal count is updated after the .call.value, it actually wasn't exploitable because of the require balances from line. So basically nobody had an initial balance aside from my coworker. So nobody was ever actually able to call this function and withdraw anything other than what they sent into the contract. So it was kind of zero sum for everybody else aside from my coworker, who could always withdraw the full amount. And somebody tried to, so this was deployed on the Ethereum mainnet. Somebody tried to hack it within an hour. So there's people out there scanning and trying to do this autonomously. Here's another example, but I'm going to skip through this a little bit. This example, again, feel free to consult the slides later, but this example is a little bit interesting and it does kind of speak to the language discussion. Basically what's happening here is, they called out to what purports to be a logging contract. So they do some innocuous sort of operations and then they log like success or something like that. But they're calling out to this external contract, whose source appears to be innocuous, but the bytecode behind that source actually doesn't match what is on Etherscan. Has anybody taken a look at Etherscan before? Anybody here? Yeah. Okay. Cool. So Etherscan is a blockchain explorer for Ethereum, and among other things, you can take a look at source code of smart contracts that are deployed on the Ethereum mainnet. But they're limited in terms of how they can do validation that a particular piece of source code actually matches the bytecode that's on chain. Namely, what they do is if you upload source code, you tell it which version of Solidity you use to compile the bytecode, and if it matches the bytecode that's actually on chain, then they give you a green check mark. But there's some quirks there. So in this particular attack, they were able to get Etherscan to disagree with what was actually on the blockchain in terms of bytecode. So if you took a look at what was verified source, it actually wasn't the logic that was being done. And in that log function, in that log contract was a backdoor where they just withdrew all the funds. All right. And here's another simple example. This one's a lot simpler. They just put a lot of whitespace in their contract so that you would have to actually scroll down in order to see the backdoor. And this caught a bunch of people as well. All right, let's go ahead here. So some takeaways here. Again, by default, everything on the blockchain is public. You really have to try to make things not public. And forever. There's no perfect forward secrecy. This isn't Signal. This isn't something else. Well, it is similar to PGP, for example, I guess, but yeah. So everything by default is public on the blockchain. Formal verification can help, but we've seen so formal verification is taking source code and doing some fancy math to make sure that the bytecode that is spit out conforms to the developer's intentions, which sounds a little nebulous, probably because it is. You basically have to codify your intentions very specifically, and you can't, if you make a mistake in codifying those intentions as well, perhaps you miss the bug that you put in your code. So for any non-trivial contract, what I would recommend is you build in some sort of upgrade path, which is, again, not the default by any means. You wouldn't run a browser nowadays that had no way of updating itself, right? But that's effectively what you're doing when you're sending money to smart contracts in the Ethereum blockchain, is you're sending money to something that might be vulnerable, is in some cases outside of the realm of what we can verify right now, and can never be upgraded. So if something is discovered, you need to fork, or you need to get people to move everything off to another contract swiftly. And finally, safer languages make for safer contracts. So the move from Solidity to Viper is going to help with this, and we're seeing this in other spaces as well. So moving on down the chain here, it's turtles all the way down. So the next level is the blockchain itself. So we talked about smart contracts that are executing on top of Ethereum. Now let's talk about EOS. Is anybody here familiar with EOS? Hopefully a fair number of people. Okay. A few people. Yeah. So when you're building a blockchain, there are a few kind of core requirements. You need to be Byzantine fault tolerant, which basically means, well, I'll quote, condition of a computer system, particularly distributed computing systems, where components may fail and there is imperfect information on whether a component has failed. So you need to be resilient in the face of this, right? In a distributed environment like a blockchain environment that has arbitrary Turing-complete execution on top of it via smart contracts, you really need to take into account any particular node can turn malicious or go offline or collude with other nodes at any given time. You need to build in, obviously, consensus mechanisms that incentivize the same sort of behavior that you actually want to get out of the blockchain. And it's really important to have a reference implementation. So, there's been a lot of white papers for various blockchains. Not all of them have actually made it to implementation, but when you're doing an implementation, you typically talk about resource requirement. How fast is it? How much memory? How much CPU? And I would say you need to build security as a functional requirement as well. So let's talk about EOS. So EOS basically didn't do any of this right. But is somehow worth billions of dollars. So EOS has a governance model, where, it's distributed in some senses, but not distributed in the senses that matter. So EOS has a number of nodes that are called block producers, and those block producers are the only nodes that are capable of mining or signing a block into the EOS blockchain. So if you want to transmit EOS tokens from one person to another, these block producers at some point need to come into contact and actually sign that transaction for you. These block producers are elected by token holders, so it's kind of a proof of stake in that sense, where they elect these block producers. But the way that this falls apart is these block producers kind of sign on to a constitution, so to say, governing how they're going to behave. And part of that constitution is a blacklist where if somebody's EOS account or smart contract was hacked and the attackers are trying to drain that account of all of its money and transfer it elsewhere and then liquidate it on an exchange, they would blacklist transfers from that account, right? So say account OXABCD was hacked, they might add that account to the blacklist so the attackers can't actually move funds out of that account, meaning the block producers will refuse to sign transactions moving funds out of the hacked accounts. So this falls apart because if any of the block producers, which again are elected by the community on a rolling basis, I forget how often new block producers are elected, but if any of them get this blacklist wrong, then that transaction might go through, and this whole thing kind of just falls apart. So of course this happened. That's not really surprising at all. So somebody stole $7 million when one of the block producers didn't implement the blacklist properly. In the slide notes for this, there's a link to Vitalik Buterin's blog on perhaps some better. It was actually a collaboration with Eamon, who's the author of this tweet, on better Byzantine fault-tolerant algorithms that can achieve 99% Byzantine fault tolerance, which is pretty cool. In addition to that, so they released a reference implementation. They released the EOS client, which was written in C++, which is a notoriously insecure language. And they opened a bug bounty on it. So for those of you familiar with HackerOne, that may look familiar on the left-hand side. They opened a bug bounty on this EOS client, again, for this multi-billion-dollar blockchain. And within the first week of opening this bug bounty, they got, from one person, they got 12 remote code execution vulnerabilities reported. Each one they awarded $10,000. So this one guy, Guido, reported 10 remote code executions vulnerabilities in the EOS client within the first week, any of which could be used to steal the private keys of anybody else on the network. So, if he was a little bit more nefarious, he could have just stolen millions and millions and decimated the value of the entire blockchain. In addition to that, Kihu 360 reported a bunch as well, and they said, they actually used the word decimate as well. Okay, that such an attack could decimate the entire cryptocurrency network. So it bears repeating, but for some reason people don't seem to get that unsafe languages are unsafe. So if you're writing something that's going to be protecting, governing, kind of, working with billions of dollars worth of cryptocurrency, maybe don't write it in C++, right? Let's move to, nobody's perfect. People will make mistakes. So let's move to something else. So some takeaways are many dimensions to a trustworthy blockchain design, both in terms of design and implementation, and neglecting any of them can be catastrophic. And rule number 2, which is rule number 1 of cryptography, is don't roll your own cryptography. So EOS did this as well, by the way. IOTA is another great example of that if you like cryptography and how to do it wrong. Okay, so moving along, exchanges. So to actually use a blockchain, a lot of people need to move funds into the blockchain, out of the blockchain, and they accomplish this with exchanges, right? Not everyone's mining Bitcoin on their computer, 10 years ago. That was 10 years ago, yeah. And this has serious real-world implications. So there was a UN report recently where North Korea is funding its weapons programs to about the tune of about $2 billion via cyber. And a lot of that is actually coming from hacking cryptocurrency exchanges. Presumably because of the lack of language and cultural barrier, a lot of those exchanges have been in South Korea. But they're not only in South Korea, some have been in Japan and elsewhere. So this is a serious kind of pressing issue and, more of a geopolitical one than simply hacking a smart contract, because this is a significant amount of funds that could be falling into the wrong hands. So this is BitThumb, that was legitimately hacked. So they lost around $13 million. This one, so there's some that get hacked, and then there's others that just exit scam. So this was a Canadian exchange where the CEO was the only one that held the private keys for the exchange wallets. And so he mysteriously disappeared. Some people claimed he died. But it was investigated by Ernst & Young along with the Canadian authorities, and they found that the exchanges, the funds from the exchange were actually used to collateralize margin accounts for the CEO of this exchange. And anyway, this exchange went bankrupt because nobody had access to these funds aside from the CEO, which he used to just kind of YOLO gamble on the side. So that's also really bad, from a, this is still a security issue, right? People need to have confidence in exchanges in order to do business in the blockchain environment. So even though this is not really a cyber attack necessarily, it's still an attack on reputation. That's not good for usage. So, a little bit ago, actually at DEF CON this year, Coinbase gave a great talk. They actually captured several Firefox 0 days that were targeting their employees, and they gave a presentation on those 0 days and a little bit about how they discovered them. So, if you're going to be working for an exchange, you're going to build an exchange, what exchanges need to do is a lot of defense in depth. They need to deter lateral movement. If you're kind of the apex defender, you need to be catching 0-day attacks like Coinbase is doing. And what they needed to do, in order to do that is they were gathering data proactively, sufficient data, that they were able to actually isolate and take a look at the workstations that were hit by this particular 0-day exploit. There's actually 2. I believe it was a renderer and then a Provisk. And use hardware security modules and audit access to them. And finally, when all else fails, if you assume compromise, limit your exposure, right? So, don't keep all your funds in the hot wallet, right? Transfer them to some cold storage wallet. So even if the hot wallet's compromised, you're not totally out of luck. And finally, regulation is pretty essential for trust. So, at least in the States, we have, some very well regulated exchanges. And, so anyway, that's essential for trust, and particularly people that are not already, kind of motivated to be in the blockchain space in the first place, right? These are the moms and pops that want to, open a Coinbase account, much like a bank account sort of thing. So moving on down, talking about workstations and ecosystem, this could really be an entire talk. Obviously, this covers like the full gamut of what are you doing, what are you running when you're talking with blockchains, what is running on your laptop, what is running on your phone. But these are all critical to securing this ecosystem as well. So again, this could be kind of a whole talk, but Trail of Bits recently was doing some great work in this space on two-factor and WebAuthn, adding that to package managers like Python's pip manager or PyPy. That needs to happen in more places. WebAuthn is, if you have those USB sticks, Google markets one called Titan. Yubico has other ones. They're invulnerable to phishing because they're not going to be confused like a human is, and they're not going to respond with the correct response to an incorrect domain, right? So building that kind of thing into whatever web app you're building, that helps. Reproducible builds, this is another big one. So some Linux distributions have been working on this for a while. Debian is kind of leading the charge on this front. They actually have a burn down chart in terms of the number of number of packages in their official repository that remain not reproducible, and it's going down. And something like over 96%, I believe, of packages are now reproducible. And what that means is, given source code and given a binary, you can prove that binary came from that source code. Right? If you cannot do that, and by default a lot of software is not reproducible, then you cannot make guarantees about the binary based on analyses you do on the source code. Right? So this is pretty critical. And one of the, an example here is Python bytecode is not reproducible, and Python bytecode is shipped in a lot of Linux distributions for various purposes, but reproducible builds has, huge implications on a lot of different fronts, including the next item here. So if you're doing some sort of security checks, some sort of automatic or static or dynamic analyses on your source code in some continuous integration environment, if you don't have assurances that source code matches what binaries people are actually using, then the chain's kind of broken, right? So you can do those checks on the source code, but again, people would have to trust that the binary they're running on their system has not been interdicted, has not been, backdoored. Perhaps, somebody compromised a developer, for example, and that blends in well with the next point. Say somebody compromises a developer account that publishes a package that a lot of software uses. They can selectively backdoor the software that other people rely on, and this has happened many times. So in particular, Node or the NPM ecosystem is pretty notorious for this. They're doing a lot of work to try to shore this up right now. In fact, they actually rolled out 2FA and WebAuthn. But they've had many problems. One, did anybody hear about Node.js's left pad issue? Okay, so what that was, okay, cool. So what that was is, so Node.js, you can use Node.js to write, offline applications or web apps that are actually hosted somewhere, whatever. But when you're importing libraries that other people have used for convenient functions, these functions can range pretty severely, but this one particular function that everyone was importing was left pad, which all it did was took a string and added a certain amount of spaces to the left-hand side of that string. And apparently a lot of JavaScript developers opted to use somebody else's implementation of this left pad function in order to actually go about doing this. So it's a very simple sort of piece of logic, but instead of writing it again, everyone just used this left pad package. And this left pad package, the maintainer deleted the package, and all the other packages that relied on this one broke. And another problem associated with this is somebody could have republished the package in the same name, a malicious package in the same name, and then backdoored all the other software that relied on that package. So there's actually a quote on this. There are only two hard things in computer science: cache invalidation and naming things. So this kind of falls under the second one in terms of naming things. Okay. The last sort of section on this is hardware devices, so hardware security modules and other devices. So this was a fun development a few months ago. Ledger, which produces some cryptocurrency wallets, hardware wallets, they spun up a vulnerability research team, and the first thing they did was target unfixable hardware bugs in their primary competitors' products, namely Trezor. So Ledger found some bugs in Trezor devices. Given physical access to a Trezor, they were able to, with about $100 of equipment, extract the seed from the device. And yeah, if you're interested in these sort of attacks, I'd encourage you to take a look at the slide notes on these, because there's a lot of details here. But it takes less than 5 minutes and around $100 to recover a seed, which is, the random number that is the genesis of the keys that are held inside of that hardware security module. And in response, Trezor wrote a blog post, and the picture on that blog post is literally shots being fired at them. And what they said in summary is they knew about this from the beginning, but they didn't actually care too much. They didn't think a lot of their users cared sufficiently, or they didn't prioritize physical attacks relative to things like remote attacks. So, for the devices that are currently out there, for the most part, they're not hardened from a physical access sort of standpoint. So that's something important to know, and it's not something that's very widely advertised. Excuse me. So Trezor in that blog post said, there's a bit of disdain probably in the voice on this, is we would like to thank Ledger for practically demonstrating the attack that we had been aware of since designing Trezor. So anyway, there's a little back and forth there. So they've done a number of other awesome pieces of research. I'd encourage you to check it out. It's called Ledger Donjon, if I'm pronouncing that correctly. I don't know. Some other great work has been wallet.fail, which is actually a URL if you go there. You can take a look at some of the work that they did. And I'm kind of blowing through this right now because there's a lot of work on this front. Salim Rashid has done some great work as well. As a teenager, he was breaking all kinds of devices. In this case, it was Bitbox. So they also took a look at other more standard kind of HSMs, things that you might deploy in a cloud, or rather in a data center sort of environment. Anyway, so going back to this, so the bugs that they found in this more off-the-shelf sort of HSM had memory corruption vulnerabilities that are reachable remotely in daemons that were running as root in a Linux kernel from 2009. And they had no exploit mitigations really turned on either. There was no ASLR, there was no stack cookies, there was no nothing. So this HSM, which they did not name, but it's really trivial to find out which HSM they're talking about. They owned it through and through. There was like 8 different daemons listening, and they found a number of 14 different vulnerabilities in a fully unauthenticated attack surface running as root. So here's another great Twitter quote here. Tell me again how C isn't the problem. So Microsoft published a piece of research where 70% of all security bugs, at least in their products, have been memory corruption vulnerabilities or memory safety issues more generally. Matthew works at Google. He's saying no way to prevent this, say programmers of only a language where this regularly happens. So again, let's move to safer languages. Let's not code blockchain things in C and C++, or HSMs, perhaps. So in terms of, the kind of knee-jerk reaction a lot of times when, people say, don't use C, don't use C++, is what about mitigations? In the case of the last HSM that I was briefly talking about, they didn't enable mitigations anyway, but if they had, Halvar published this is from a talk that Halvar Flake gave some years ago, where what's being graphed here is the difficulty on the y-axis. I'm not sure why it's not labeled, but difficulty in exploiting a particular target, right? So as more research is published, as people get better and better at taking a look at a particular target, it becomes easier and easier to hack that target. Then a new mitigation is introduced, and the difficulty goes up. And this is what people think the effects of mitigations are, but what it really is, the difficulty goes up, and then people find a bypass for that mitigation or some generic sort of copy and paste code that they can reuse across their exploits. And at the end of the day, it kind of evens out a bit. So, you get kind of a short-term bump, but it's not a long-term solution. The long-term solution is not providing programmers with the tools necessary to build in vulnerabilities. So the last thing I want to talk about in this section, has anybody here heard of BitFi? Yeah, okay, in the back. So enough said. BitFi is, I guess it still exists, a brain wallet, which means, so this device basically does nothing. So this device, they're selling this wallet, which is allegedly a hardware security, it's supposed to compete with Ledger and Trezor and things like that. What it is, it's a MediaTek Android device with the Wi-Fi and the camera removed and an app on it where you have to remember your passphrase. So really this device could be replaced with a Python script, and people actually did that, because there's nothing about your keys, your cryptocurrency keys, that live on this device. They don't really get security in general, but so they issued. So this was kind of a fun little Twitter saga. John McAfee, if you're familiar with him, was endorsing this product. Offered a $100,000 bounty if somebody could hack it, and so somebody did, right? And their Twitter was saying, rooting the device does not mean that it was hacked. So I'm not really sure what hacking really means in this context. But to be fair, they updated their Twitter profile to say that social media is not checked for accuracy by their engineers. So they're good now. Some other research on that front. Again, Salim Rashid. Hope I'm pronouncing that correctly as well, and a few others. So a lot of references to take a look at when these slides are published. Happy to chat afterward as well. So let's flip on the other side now. So now that we've talked a little bit about how things can go wrong, securing a blockchain sort of stack all the way from smart contracts down to the hardware, what can we use blockchains for to build in the security space? So there are a few different categories that I'll touch on real briefly. So we can use blockchain for identity authentication and auditing, right? So there's a project called Civic that's kind of a blockchain-backed identity management, KYC sort of platform, which is pretty interesting. I work for PolySwarm. The PolySwarm co-founders also work for a company called Narf Industries, which did work on a DHS project for building blockchain-backed identity authentication and basically selective information disclosure using blockchain. So DHS wanted to use blockchain to kind of have a bit of a better handle on their employees accessing various secure sites and selectively revealing attributes of those employees to maintain a limited need-to-know sort of basis. So this was for DHS's own employees going to various sites and only revealing what they needed to in order to actually get access to the information that they needed. In the supply chain management area, so Walmart famously uses Hyperledger Fabric to track the provenance of leafy greens. These are things like lettuce. They actually rolled this out, not too long ago, romaine lettuce in the United States and Canada was recalled for about a month. And they, but at the time, I don't believe Walmart was using this at the time, but the idea of using a blockchain to kind of track where food is coming from would allow people to more quickly narrow down where, in this case it was E. coli in lettuce, narrow down which farms the infected lettuce came from, and then they could pull stock only from those farms and not just pull from all of North America, right? Which is actually what happened. Another interesting thing, we're in Abu Dhabi. Abu Dhabi's national oil company is tracking oil movements on chain. So that's awesome. And De Beers is tracking diamonds. So that's pretty cool. Another way you can go with this is creating, creating security marketplaces. So there's another project called QuantStamp, which is encouraging or incentivizing security researchers to identify and report vulnerabilities in Ethereum smart contracts, and it rewards them for doing so. And then what we're building at PolySwarm is a marketplace for discovery and identification of new malware. So I'll talk about that real quickly. Basically what happens on PolySwarm is it's an economic competition where antivirus engines compete to detect malware. So an enterprise customer might upload a piece of malware and engines weigh in saying, I think this is malicious or I think it's benign. And they actually stake a certain amount of tokens along with that response. Depending upon if it actually was malicious or if it actually was benign, the incorrect side of the market, their tokens are taken and given to the correct side of the market, right? So it encourages people to stay on top of the latest threats and only respond when they're actually confident in something. This is kind of what it looks like. And I have a link at the end. But so a few takeaways. So we need more easy-to-use formal verification. We need it enabled via more secure languages are one way to get there. Exploit mitigations are a stopgap at best. We need to do more fuzz and so dynamic and static checking in CI in continuous integration, but crucially this does not displace human audits, right? We need creativity, and computers are notoriously bad at creativity. So we need creativity to drive what the next generation of CI tests are. We need to be clear about defended threat models and expressing those defended threat models in layman's terms. So, at least when I was building this slide deck and I was taking a look at Trezor's website, there was nowhere, at least prominent, that was saying, make sure you don't leave your Trezor at home or, someplace at a hotel room or something that, somebody might come and physically access, because that is not something we're defending against. We should be honest, and upfront about those things and let people make informed decisions. And we need better cloud HSMs that support crypto assets, so there aren't many out there. And the ones that are, again, this is not unusual. This one that Ledger took a look at that had a bunch of remote code execution bugs and a memory unsafe daemon running as root. This is unfortunately the rule rather than the exception even today. We need to improve the security resiliency of our development ecosystem. So a tweet I saw right before coming on stage actually is some research from the Technical University in Darmstadt. I hope I'm saying that right. Published some research where they did a bunch of graph analyses on NPM packages, so JavaScript node packages. And they found that if you compromised only 20 developer accounts in NPM, you could take over half of all published packages in NPM. And if you compromise some other portion of that, you'd still take over a massive amount of the internet. So we need some more resiliency there. And finally, blockchains hold significant promise as foundations for security in terms of products and services. But if you can't trust those blockchains because they have security problems, then you can't get anywhere. So blockchains need to be trustworthy first. And if they're trustworthy, perhaps we can build interesting security products on top of blockchain. So thank you. That's my talk.
Thank you, Paul. Are there any questions from the audience? If there are not, then we'll go straight through to the Slido.
Okay, first one. Vulnerabilities appear more because of the EVM bugs or because of the programmer mistakes? Definitely the programmer mistakes. So if there was so an EVM bug might refer to, say, Go Ethereum or Parity or some other Ethereum client interpreting EVM bytecode incorrectly. That hasn't happened on a large scale so much, and the bytecode is rather simple. It's kind of like Java bytecode; it's rather simple, so that is a possibility. But it's much more the programmer's mistakes. Next question: do you think WebAssembly will make smart contract more secure? I think I know where this question's coming from. Yeah. So I mean. I'm not, let's see. So yes, I think really any kind of language that is more security minded, so Solidity was kind of born, so Solidity, the language that most smart contracts are written in, was kind of born out of necessity and was designed to be most, they needed a language to build smart contracts in, and they kind of rolled one real quickly. And they recognized that most people hip Web 3.0 people like JavaScript, so they kind of coded it around somewhat resembling JavaScript, although it's different in some key ways. So, it wasn't from the get-go, it wasn't a security-focused sort of language. And as you saw in some of the examples, if you simply named your constructor function incorrectly, then you would have totally unintended behavior inside of your contract that lived on the chain that anybody can exploit. Those sorts of things, those sorts of foot guns, that with another language, perhaps WebAssembly or Viper is the one I go to. I think anybody's going to do a better job than Solidity. So, okay. What are the safe languages available for Ethereum? So kind of just cover that. If you're starting out, so Viper is currently in beta, although and that's Viper, VYPER, for like Python. If you're just starting out, I would encourage you to study both Solidity and Viper. Those are the main ones. But if you're going to be coding smart contracts, I would encourage you to code them in Viper, although most are currently in Solidity. So if you want to take a look at what's currently out there, you kind of have to know Solidity. Okay. And how did EOS garner such support despite its core issues? Namely, C++ is a primary language, perhaps lack of consumer knowledge regarding blockchain security or scalability of the product. So a lot could probably be said on why EOS is popular. It's, they did a lot, I guess I would say they did a lot of things right in terms of marketing, their blockchain. But there's kind of a tipping point in terms of, when people invested in or, bought pre-sale tokens in EOS, they wanted other people to buy more tokens, right? And EOS was structured such that their token sale was a rolling token sale over the course of a year, I believe, with discounts decreasing every week, something like that. Don't quote me. It's similar to that though. So anybody that had put money in wanted other people to put money in the next week, right? They're going to have a less favorable exchange rate, and immediately whatever they put in, their investment is going to be worth more. So it was kind of encouraging this sort of snowball effect where you had a lot of people online trying to get other people to buy EOS tokens. And this was back when, you know, they didn't even have a public implementation. So C++ or otherwise, they just didn't have an implementation when they were doing this, at least initially. And yeah, so I think it's primarily around the hype, more than anything else. People wanting other people to buy US tokens at a less favorable exchange rate than they were getting. I think that's really the core of it. Okay. All right, one just disappeared, but will security of Hyperledger Fabric any known attacks? That's a great question. So to be frank, I've studied Hyperledger a bit less than Ethereum. You know, what we're building at PolySwarm is based on top of Ethereum. But Hyperledger, you know, it's a lot more customizable than Ethereum. You know, it's kind of, you can run it in a private consortium sort of manner. You can run Ethereum that way as well, but not many people do that. But it's more geared toward that sort of enterprisey, less, you know, it's not necessarily geared for public implementations of a public blockchain, right? You're not going to have random people mining on a Hyperledger node, right? Hyperledger is going to be used as a building block to build what it is that you want to do in an enterprise environment. So in terms of any known attacks, yeah, I'm sure there's some, but I don't know offhand. I'd have to check. Will Python evolve to be a better tool for blockchain? Yeah, I'm not entirely sure what's being asked by this question, but yeah, I interact with a blockchain environment using Python on a fairly regular basis. Again, Viper it's not based on Python. It's just trying to have Python-like syntax, in the way that you write smart contracts. What's nice about Viper is it removes the ability to, for example, inline assembly. So in Solidity, you can actually, like in C, you can drop to inline assembly. In the case of Solidity, it's assembly for, the EVM assembler. Whereas, you know, in C, it would be assembly for, you know, the x86 assembler or whatever architecture you're building on. You can't do that in Viper. And you can't do a lot of other things that make it very difficult for formal analysis to make any kind of guarantees. So removing those sort of functionalities, is what is nice about Viper. But Python, I mean, I don't know. I like Python. I'm not sure it needs to change much for blockchain, but, all right, so access to HSMs and advanced crypto tools or training is not equal across the world. Do you think that would change anytime soon? Deep question, a bit more philosophical, I think. Oh, and another one popped up. So, yeah, not equal across the world. No, I don't really think that'll change anytime soon. So if we're referring to HSMs in terms of ledgers, nanos, the things that you put in data centers, you know, I don't really think that'll change much anytime soon. You know, that's more of an economic kind of question and also, you know, legal sort of question. But, you know, even without having ledgers or nanos, you can always do things like having a cold storage wallet, right? You could write something down and put it in a safe. You know, maybe you want to put part of your key in one safe and part of your key in another safe. I don't know. But ultimately, you know, these devices, at least some of them aren't designed to resist physical attacks anyway, right? So, it would be nice if everyone around the world would have access to things like ledgers and Trezors, but I'm not sure what would be happening right now to change that at the moment, unfortunately. I don't know what would be changing that. Okay, is Facebook Libra losing key partners an indication that more large projects are not doing well too? Good question. So I think one of the reasons, oh, and perfect timing, I have 45 seconds left. One of the reasons Libra is losing key partners is the implications of Libra are pretty broad and pretty impactful from a monetary policy standpoint of a lot of governments, right? You don't really want to have a Facebook coin. They already have a lot of power in other sort of aspects, and allowing them to have power in that aspect as well is probably not something that's, taken very, not something that's welcomed by a lot of governments. And you'll notice a lot of the people pulling out of the Facebook Libra project are, I think it was like Visa and MasterCard or something. They're pulling out because, these are real companies with real operations in real countries, and they're going to be pressured by those countries, right? So they don't want to, so ultimately, what we're talking about here is a lot of tech companies and, banks, et cetera, coming together, trying to create a new currency, and world governments are kind of like, whoa, whoa, whoa. That's kind of our purview. So I'm not sure if that's an indication that other large projects are not doing so well either. I guess it kind of is a question of what are the other large projects doing? If they're not trying to, if they're not going to butt heads up against somebody that regulates the people making the new coin, then maybe they would do better. But in this particular case, they're kind of running up against, what is typically a government's sort of purview. So I think that might be why that's happening. All right.
Thank you, Paul Makowski. Can we please have a big applause for him?